You know, when you think about the most famous villains in medical history, they usually have like a very distinct face.
Right. Yeah, you know exactly who you're fighting.
Exactly. You get a diagnosis, and it's this specific singular enemy, like polio
Mm.
or tuberculosis, smallpox.
Because they're single entities.
Mm.
You know, you can isolate them, quantify them, and eventually build a targeted defense against them.
Yeah, you look at it under a microscope and boom, there it is. But then you look at the greatest, most pervasive nuisance in human history, right? The thing that takes us all down multiple times a year.
Oh, yeah, the thing that clears out offices and, shuts down classrooms.
Right. And suddenly the villain doesn't have a face at all. We just give it this generic name, wrap ourselves in a blanket, and surrender to the couch for a week.
It really is the ultimate invisible enemy.
Right.
And, I mean, because we are so used to it, we completely underestimate the staggering biological complexity that it actually takes to make you that miserable.
So true. Well, welcome to today's deep dive. Our mission today is to basically unpack a massive stack of virology research, medical history, and clinical data to explore the most frequent infectious disease experienced by human beings. We are taking on the common cold.
Yeah, and specifically, we're going to look closely at the main culprit, which is rhinovirus,
Yeah.
and all of its viral friends.
Rhinovirus and friends, yeah.
Exactly. We'll explore the brilliant first principles biology behind why colds happen, the history of how we discovered them, and, the deeply misunderstood mechanics of why you actually get sick.
Because, I mean, let's face it, you're only going to catch 2 to 3 of these things this year, and if you have young kids, oh man, you're catching even more.
Oh, absolutely. So many more.
Right. So it is time you actually meet the enemy. But before we can map out a battle plan, we have to define what we are actually fighting. And the first major shock in the medical literature is that the common cold does not technically exist.
I love this point. It really doesn't. Not as a single disease, anyway.
Yeah, so saying I have a cold is medically identical to saying I have a headache. It just describes a pattern of symptoms you're feeling, but it tells you absolutely nothing about the specific, microscopic culprit causing it.
And that is the crucial foundational concept for this entire deep dive. I mean, the common cold is a clinical syndrome. It's just a massive umbrella
Yeah,
label.
for it, umbrella.
Medically speaking, it's defined simply as a mild, self-limited upper respiratory tract infection. It lasts, roughly 7 to 10 days. And it's marked by the specific body part that gets infected and a familiar cluster of symptoms.
Right, the classics. Congestion, runny nose, sneezing, sore throat, and notably, low to no fever.
Exactly. Low to no fever is key. It's categorized entirely by what it does to you, not by what it actually is.
Which makes sense historically, right? Given that for centuries, doctors had no idea what viruses even were.
Oh, totally. I mean, just look at the name itself. The word cold is this linguistic fossil of humoral medicine.
Wait, humoral medicine? Like the 4 humors?
Yeah, exactly. Before the germ theory of disease solidified in the late 19th century, the literal folk belief was that exposure to cold air or dampness directly caused the illness. The idea was that a physical chill disrupted your body's internal balance, your humors.
So, like, you let the cold air in, your humors get thrown out of whack, and your body reacts by, I don't know, producing a bunch of mucus to purge it.
Precisely. That was the actual medical consensus. Then, as virology matured in the 20th century, the definition shifted radically. It became strictly virological.
Meaning they finally defined it by the actual virus.
Right. It was defined as an infection of the nasal and pharyngeal epithelium by a respiratory virus. But in modern clinical practice, the definition has widened back out into this massive umbrella diagnosis, mostly because the symptoms overlap with so many other conditions.
Yeah, distinguishing between a cold and something else is like entirely about boundaries because influenza, for example, shares some symptoms but is far more severe, right? It's systemic and comes with a high fever.
Absolutely. Flu is a whole different beast.
But then what about allergic rhinitis? I mean, hay fever perfectly mimics a cold with the runny nose and congestion, but it's clearly not a cold.
Because there is no pathogen in hay fever. That's the boundary. Allergic rhinitis is triggered by your immune system just overreacting to allergens like pollen or dust.
Right, so it's a completely different mechanism.
Completely different. It operates on a pathway involving IgE, which is the specific antibody your body produces during an allergic reaction. That triggers histamines. So there is no infectious agent, no virus replicating, and no fever.
It just feels the exact same.
Right. And obviously, since 2020, distinguishing between a cold, the flu, and COVID-19 has become a much more urgent public health question. because they all present with that overlapping upper respiratory misery.
Yeah, that upper respiratory misery is the worst. So, okay, if the common cold is just a symptom pattern, an umbrella term, who exactly is standing under that umbrella? Because the virology data here is just wild.
It really is. It identifies rhinovirus as the single largest contributor. It causes an estimated 30 to 50% of all adult colds.
Okay, but wait. If one dominant virus is causing almost half of our colds, why doesn't catching it once grant us lasting immunity? Because we build immunity to other viruses. Is rhinovirus basically just like dozens of different viruses wearing a trench coat pretending to be the same guy?
I mean, your trench coat analogy is biologically perfect. But we need to look at how that disguise actually works in practice.
Mm.
Rhinovirus belongs to the Picornaviridae family.
The Picornaviridae family. Okay.
Yeah, and these are incredibly small, non-enveloped RNA viruses.
Let's break that down for a second. Non-enveloped RNA. What does that actually mean for, how the virus behaves?
So an enveloped virus, like influenza or SARS-CoV-2, has a fragile lipid outer layer. It's basically a layer of fat that is easily destroyed by soap or just by drying out.
Oh, so that's why hand sanitizer works so well on them.
Exactly, but rhinovirus is non-enveloped. It doesn't have that fragile fat layer. It is essentially this microscopic payload of RNA genetic code protected by a really tough geometric protein shell.
Wow, so it's basically armored.
Yeah, that makes it weirdly resilient outside the body. But more importantly, within that rhinovirus family, the virus is broken down into over 160 distinct serotypes across 3 species: rhinovirus A, B, and C.
160 variants. That is insane. So when my immune system fights off one of them, it learns absolutely nothing about the other 159.
Nothing at all. It's a completely blind spot. When you get infected, your immune system eventually generates neutralizing antibodies. Those antibodies are designed to target and lock onto very specific outer capsid proteins.
The capsid proteins. So that's the armor you mentioned.
Exactly. Think of them as the 3D armor plating on the outside of the virus. That armor acts like a unique fingerprint, but those capsid proteins mutate and differ substantially from one serotype to the next.
So the immunity you build against, rhinovirus type 14
Is structurally useless against the armor plating of rhinovirus type 89.
Exactly.
Man, that reframes a massive misconception for me. Because when you catch your third cold of the winter, the instinct is to think your immune system is failing or weakening somehow. Right? People always think their immune system is down.
Yeah. But it's not failing to remember a past infection. It is literally encountering a genuinely new, completely unrecognized pathogen.
Your immune system is functioning exactly as it should be. It just hasn't seen this specific configuration of the trench coat disguise before. And honestly, this is the exact biological reason why young children catch 6 to 8 colds every single year.
Because they're basically walking around with a blank slate.
Exactly. They haven't built up a library of localized immunity to any of these 160-plus variants yet.
And rhinovirus isn't even alone under the umbrella, right? You have non-SARS human coronaviruses causing another 10 to 15% of colds, plus respiratory syncytial virus like RSV, parainfluenza, and adenoviruses.
Yep, it's a crowded umbrella.
They are completely different viral families using totally different methods of attack, but they all result in the exact same congestion and sore throat, which honestly raises a huge question.
Oh, I think I know where you're going with this.
Right. If there are over 160 variants of rhinovirus, plus all these other distinct viral families, why are they all targeting the exact same real estate? Why the nose and throat? Why don't they just, travel deeper into the body?
Well, it comes down to 2 incredibly elegant first principles biological constraints.
Oh.
The invasion relies first on a lock-and-key mechanism.
Okay, a lock and key.
Yeah, the vast majority of rhinoviruses can only enter your cells by binding to a specific docking receptor on the cell surface. It's called the ICAM1 receptor.
And that was identified by Jeffrey Grieve back in 1989.
Yes, exactly. ICAM1 is a molecule that is normally just involved in your immune system's cellular signaling. But rhinovirus actually evolved to hijack it as a doorway.
Oh, wow. Sneaky.
Very. And
Right.
It just so happens that ICAM1 receptors are incredibly abundant on the epithelial cells lining your nasal passages. The virus goes where the locks fit its specific keys.
Makes total sense.
But the second constraint is even more fascinating, I think. Temperature adaptation.
Right, because the body has different microclimates inside of it.
Exactly. Rhinovirus replicates most efficiently at roughly 33 to 35 degrees Celsius. Because air is constantly moving in and out of your nose, cooling the local tissue down, the nasal cavity sits perfectly in that 33 to 35 degree range.
Wait, so what happens if it goes lower, into the lungs?
Well, if the virus gets inhaled deeper down into the lungs, it hits the body's core temperature, which is 37 degrees Celsius.
So the virus literally cannot handle our core body heat.
It physically struggles to replicate at 37 degrees. The proteins it uses to assemble itself actually become unstable. The virus is evolutionarily tethered to the cooler microclimate of the upper respiratory tract.
That is wild.
Yeah, and this temperature limitation is precisely why a typical cold rarely descends into severe, life-threatening pneumonia the way an influenza infection can. The flu thrives at 37 degrees, rhinovirus just falls apart.
That is amazing. So it's geographically confined by our own body heat. But, okay, if the virus is just statically hanging out in our nose, failing to move deeper, why do we feel so systemically terrible? Like the brain fog, the massive congestion, the absolute misery.
Well, because the virus isn't causing the misery. You are.
Wait, what?
The symptoms you hate are largely friendly fire. When the virus binds to that ICAM1 receptor and enters your cells, your body detects the invasion and triggers an interferon response. It basically rings an inflammatory alarm bell.
Ah, inflammation, the root of all evil.
Exactly. That inflammation forces the blood vessels in your nose to swell, which is what causes the physical feeling of congestion. It's not actually mucus blocking the airway at first, it's just swollen tissue.
Seriously, it's just swollen tissue.
Yep. And then your body drastically ramps up mucus production to physically flush the viral particles out. The misery is literally just your innate immune system aggressively doing its job.
Man, it's wild to think the virus is trapped in the nose by body heat, while our own immune system is just blowing up the surrounding tissue to get rid of it. But if it's trapped up there in the nasal cavity, how on earth is it getting out and infecting the rest of us?
That's the million-dollar question.
Right, because the classic cinematic visual is someone sneezing on a crowded bus, and this dramatic cloud of aerosolized droplets just drifts across the aisle. But the history of how we actually prove transmission tells a very different story, doesn't it?
It really does. And the history is this masterclass in scientific deduction.
Yeah.
It starts way back in 1914 with a German bacteriologist named Walter Kruse.
Okay.
He took nasal secretions from a colleague who had a severe cold.
Ugh, which is incredibly gross, by the way.
Oh, I know. Medicine is often very gross.
Mm-hmm.
But Kruse took those secretions and passed them through a porcelain Chamberlain filter. These filters had microscopic pores that were small enough to trap every single known bacterium.
So whatever comes out the other end has no bacteria in it.
Right. So he took the resulting bacteria-free liquid and dripped it directly into the noses of healthy volunteers.
Oh, those poor volunteers.
Seriously. But when they developed colds, Kruse definitively proved that whatever was causing the illness had to be a filterable agent smaller than a bacterium, a virus.
But proving it was a virus and actually isolating it, those are two completely different things.
Exactly. It took another 4 decades. In 1956, Winston Price at Johns Hopkins University finally isolated a specific cold virus from a medical student, which he called the JH virus. That isolate, and others found shortly after, were eventually named Rhinovirus, from the Greek word for nose.
Okay, so by the 1950s, we finally knew what it was. But that still doesn't explain the transmission. Like, how did we move from the idea of the dramatic sneeze cloud to understanding how it actually spreads? I know there was this landmark experiment involving playing cards.
Yes. That brings us to the 1970s and 80s. 2 researchers at the University of Virginia, Jack Waltney and Owen Hendley, ran this series of brilliant experiments comparing airborne spread versus physical hand contact.
Okay.
Remember earlier when we discussed that rhinovirus is a non-enveloped virus?
Right, the tough protein shell instead of the fragile fat layer.
Exactly. Because it has that tough shell, Gwaltney and Hanley discovered it is incredibly resilient on hard surfaces. They tested doorknobs, coffee cups, and in one really famous setup, playing cards.
So they just had infected volunteers sit in a room and play cards.
They had infected people handle a deck of cards, yeah. And then hours later, completely healthy volunteers would come into the room and handle that exact same deck. The researchers observed that people unconsciously touched their own faces, specifically, rubbing their eyes or their noses dozens of times an hour.
And the tear ducts drain right into the nasal cavity.
Exactly. You touch the card, you rub your eye, and you have just successfully delivered the virus's rigid protein shell directly to your own ICAM1 receptors.
That is terrifying.
It is. Gwaltney and Henley proved that hand-to-hand or hand-to-surface-to-face contact was a dominant route of transmission. The sneeze cloud happens, sure, but the contaminated doorknob is far more insidious.
Which makes sense.
Yeah, and this research fundamentally shifted global public health messaging. It became the core scientific justification for why we relentlessly push hand washing in schools during the winter.
But wait, if the primary way we catch colds is by touching contaminated playing cards or doorknobs and then touching our faces, that completely flies in the face of the most famous piece of folk wisdom in human history.
Oh, I know exactly what you're going to say.
Everyone's grandmother has told them, don't go out in the cold without a coat, you'll catch a cold. But if it's just a virus on a surface, does cold weather actually do anything at all? Come on, we all know people get sick when the temperature drops.
You have just hit on the greatest rival views debate in the history of cold research. For decades, the rigorous scientific consensus was that your grandmother was completely wrong. Cold weather did absolutely nothing.
Really? They're that sure?
Oh, yeah. And this certainty came from the work of David Terrell at the Common Cold Research Unit in Salisbury, England.
Wait, they had an entire medical unit dedicated just to the cold.
From 1946 until 1990. Yeah. And the setup was bizarre by today's standards. Healthy volunteers would get a paid quasi-holiday to stay in isolated flats for 10 days. The scientists would deliberately try to give them colds to study the progression.
Sounds like a weird vacation.
Right. But to test the weather myth, Terrell's group ran controlled experiments where they brutally chilled people. They made volunteers sit in freezing hallways after hot baths, put their feet in ice water, kept them damp and shivering for hours. And then they didn't expose them to a virus.
Let me guess. Nobody caught a cold.
Not a single one. Chilling alone, no matter how severe, did nothing. This became a legendary piece of scientific myth-busting. The textbook answer became, viruses cause colds, weather does not. Case closed.
But it can't be case closed, because lived human experience tells us that winter genuinely equals more sickness. If the virus is a seed, maybe the cold weather doesn't spontaneously generate the seed out of thin air. But could it somehow water a seed that is already planted?
That is exactly the mechanism. In 2005, a researcher named Ron Eccles at Cardiff University decided to test that exact watering the seed theory. He ran a study focusing on people who were already carrying a rhinovirus infection, but were completely asymptomatic.
Oh, so their immune systems were successfully keeping the virus suppressed.
Exactly. So Eccles took these silent carriers and chilled their feet in cold water. Over the following days, that chilled group developed full-blown, miserable cold symptoms at roughly double the rate of a control group who stayed warm.
Wait, how does chilling your feet cause a virus in your nose to suddenly explode?
Vasoconstriction. When you get physically chilled, your body's survival mechanism is to narrow your blood vessels to conserve core heat for your major organs. That systemic vasoconstriction includes the tiny blood vessels in your nasal mucosa.
Oh, I see.
Yeah. Less blood flow means a reduction in the number of white blood cells being delivered to the front lines in your nose. Your local immune defense drops just enough for that silent subclinical infection to suddenly start replicating out of control.
So, the grandmother folk wisdom and the virologists were both partially right. The weather doesn't magically create the virus, but the physical chill restricts your blood flow, dropping your immune defenses just enough to let a dormant virus wake up.
Precisely. Add to that the fact that cold weather drives people indoors, crowding them together in poorly ventilated spaces, which, drastically increases the transmission opportunities for those doorknobs and playing cards we talked about earlier.
That is brilliant. It makes total biological sense. Now, since we are breaking down myths, let's look at a few other deeply ingrained beliefs. What about going outside with wet hair?
Pure correlation, no causation. Going outside with wet hair provides no viral exposure route and doesn't lower your core temperature enough to cause that severe vasoconstriction. It just happens to be something people do in the winter, which is when we all crowd indoors and pass the virus around.
Makes sense. Okay, what about demanding antibiotics from your doctor?
Ugh, this is one of the most frustrating misconceptions in medicine. Colds are caused by viruses. Antibiotics target bacteria.
So it's totally useless.
It's worse than useless. Taking an antibiotic for a viral cold is like sending a physical lockpick to hack a digital firewall. They are fundamentally the wrong tool for the architecture. Bacteria are living cellular organisms with cell walls that antibiotics can destroy. Viruses are just genetic code hijacking your own cells.
Right, so the antibiotic is literally nothing to attack.
Exactly. Taking them for a cold does absolutely nothing for you. And worse, it drives dangerous antibiotic resistance in your community.
Okay, forget the pharmacy. Let's go to the kitchen. The holy grail of cold remedies.
Mm.
Chicken soup. Please tell me chicken soup actually does something.
I can actually validate chicken soup with rigorous biochemistry.
Yes.
In 2000, Dr. Stephen Renard and his team at the University of Nebraska published this really fascinating study. They demonstrated that traditional chicken soup measurably inhibited the movement of neutrophils in a laboratory setting.
Neutrophils being like a type of white blood cell.
Yes, exactly. Neutrophils are the aggressive first responders of your immune system. When the virus invades, neutrophils rush to the site, and they are largely responsible for the collateral damage, the swelling, the massive mucus production, the friendly fire inflammation we discussed earlier.
Wow, okay.
Yeah, and the Nebraska study showed that something in the complex broth of chicken soup slows down neutrophil chemotaxis. It essentially calms those first responders down.
So it doesn't kill the virus, but it genuinely suppresses the inflammatory response that makes you feel so miserable.
Yes, it provides authentic biochemical symptom relief.
That is amazing. So we have over a century of deep virological research. We know the exact ICAM1 receptor the virus uses as a doorway. We know it prefers a 33-degree microclimate. We have electron microscopes mapping its protein shell.
We know a lot about it.
Yeah, with all this incredible biological insight, why are we still just sipping chicken soup and washing our hands? Like, why is there no cure? If it's just a mild annoyance, why do researchers even dedicate so much time to it?
Well, researchers dedicate time to it because the economic footprint of the common cold is staggering. We are looking at tens of billions of dollars lost annually in the United States alone.
Tens of billions.
Easily. That accounts for doctor visits, endless aisles of over-the-counter symptom relievers, and massive widespread losses in workplace and educational productivity. By sheer volume of cases, it dwarfs the economic impact of many severe but rare diseases.
The economic incentive for a cure is massive then, so why don't we have one? We eradicated smallpox. Why can't we make a cold vaccine?
It goes right back to the trench coat. You cannot make a single vaccine because a single target does not exist.
Right, because of all the variants.
Exactly. To cure the common cold, you would have to successfully formulate a vaccine against 160 constantly mutating rhinovirus serotypes, plus multiple strains of coronaviruses, plus adenoviruses, plus RSV. You are aiming at a massive, shifting mosaic of entirely unrelated viral families.
It's a numbers game, and the viruses have the numbers.
They absolutely do. But, the decades of research are far from a failure. Studying the common cold actually gave us the master key to modern pandemic virology.
Really? How so?
Well, remember David Terrell, the researcher chilling people at the Common Cold Unit?
Right, the guy who proved cold weather didn't spontaneously create viruses.
In the 1960s, Terrell's team realized some of their volunteers were catching colds from a virus that was definitely not a rhinovirus. They couldn't identify it. So they sent a sample to an incredible electron microscopist named June Almeida.
Okay, and what did you find?
By looking at these mild cold viruses under the microscope, Almeida identified a totally new viral structure surrounded by a halo of protein spikes. They named this entirely separate family human coronaviruses, specifically strains 229E and OC43 because of those crown-like spikes.
Wait, they discovered coronaviruses in the 1960s just by trying to figure out why people had the sniffles.
Exactly. And that viral family remained almost completely obscure to the general public for 35 years. But then came SARS, MERS, and eventually SARS-CoV-2. By studying something as mundane and annoying as the common cold, scientists built the entire first principles toolkit.
The toolkit for handling pandemics.
Yeah, understanding cellular receptors, serotypes, transmission routes, and immune responses. That foundation is what allowed global science to pivot so quickly when severe respiratory pandemics emerged.
The common cold was literally the training ground for modern virology. That is incredible. Well, thank you for joining us on this deep dive. My perspective is completely shifted. We've gone from ancient Greek humoral medicine and chilled feet to 160 mutating viruses in a trench coat to the temperature gradients of our nasal cavities and a deck of contaminated playing cards.
It really changes how you look at a simple box of tissues, doesn't it?
It really does. But before we go, I want to leave you, the listener, with a final thought to mull over. If the common cold is actually a constantly shifting mosaic of hundreds of different viruses, all fiercely competing for the exact same real estate inside your nose, perhaps we shouldn't view the lack of a cure as a failure of modern medicine.
No, we should view it as an absolute marvel of human evolution. Your body successfully negotiates this microscopic traffic jam 2, 3, maybe 4 times a year.
It's pretty amazing.
It really is. You are constantly adapting, constantly updating a vast, personalized library of localized immunities, usually without ever realizing the true, staggering biological complexity of the battle happening right behind your face.
So next time you reach for that tissue and curse the invisible villain that put you on the couch, don't think of yourself as the helpless victim of generic illness. Ask yourself, which of the 160 ancient invaders did you just single-handedly defeat?